Dear students, welcome to all of you. Now we discuss Unit-3 Advanced Mechanics 2021 Semester 6. Question paper 2021 Advanced Mechanics Unit-3. Question 4a. Find Hamilton's equations in spherical polar coordinates for a particle of mass m moving in 3 dimensions in a force field of potential V. Here we are to use the spherical polar coordinates r, theta, phi, which are taken as generalized coordinates. Using the transformation equation x equal to r sine theta cos phi, r sine theta sine phi, z equal to r cos theta, we get x dot equal to this, y dot equal to this, z dot equal to this. The kinetic energy T is given by half m x dot square plus y dot square plus z dot square, that is equal to v square. So this is equal to half m r dot square plus r square theta dot square plus r square sine square theta dot phi dot square. And the Lagrangian L is given by L equal to T minus V. So this kinetic energy minus and potential energy V r theta phi is the potential energy. Since the Lagrangian does not contain the time explicitly, and so conjugate momenta are then PR equal to del del R dot L, and that is equal to m r dot, and p theta equal to del del theta dot L equal to m r square theta dot, and p phi equal to del del phi dot L, so m r square sine square theta phi dot. Therefore, the Hamiltonian H is given by H equal to PR r dot plus p theta theta dot plus p phi dot minus L. So after simplification, we get this is equal to 1 by twice m p r square plus p theta square r square plus p phi square r square sine square theta plus v r theta phi. Here we use the value of this r dot equal to pr by m, theta dot equal to p theta by m r square, and phi dot equal to p phi by m r square sine square theta. The Hamilton's canonical equations of motion are given by qi dot equal to del pi h, pi dot equal to minus del qi h, give r dot equal to del pr h, so pr by m, because h is this, so 1 by twice m into 2 pr, and so p r dot equal to minus del r h, theta dot equal to del p theta h, p theta dot equal to minus del theta h, and phi dot equal to del p phi h, and p phi dot equal to minus del phi h. This equals to minus del phi v. So we get 1, 2, 3, 4, 5, 6 canonical equations of motions for this Hamiltonian. Next question 4b. Explain the principle of stationary action. How does this principle lead to Fermat's principle? The principle of stationary actions states that the equations of motion of a physical system can be acquired by finding a stationary point of the action. In other words, the first variation of the action has to vanish. The principle of stationary action is also known as the principle of least action. The term least action is a historical incorrect name since the principle has no minimality requirement. The principle states that the trajectories, that is the solutions of the equation of motions, are stationary points of the system's action functional. Mathematically, this states that capital delta integration T1 to T2 summation I equal to 1 to n pi qi dot dt equal to 0, where W equal to integration T1 to T2 summation over I pi qi dot dt is called Hamilton's characteristics function or abbreviated action. And this is the principle, the stationary action or principle of least action. This now the how does this principle leads to Fermat's principle? Fermat's principle: the actual path taken by a light ray between two fixed points makes the travel time of the ray stationary. That is, the time taken is extremum. And deduction from the principle of stationary actions for conservative system, the Hamiltonian is constant and the potential energy is independent of time. So Pi equal to del del Qi dot L equal to del del Qi dot T minus V. So del del Qi dot T, because V is independent of Qi dot. Therefore, summation over I Pi Qi dot equal to summation over I del del Qi dot T Qi dot. This is equal to 2T. And hence the principle of stationary action 1, and this is the action 1, which is principle of stationary actions 1, takes the form delta integration T1 to Tt 2T dt equal to 0. Therefore, delta integration T1 to T2 T dt equal to 0. This is another form of principle of stationary action in case if there is not any external force on the system, its kinetic energy T as well as the total energy H will be conserved. Then from 2 we get delta integration over T1 to T2 dt equal to 0. That is delta T2 minus T1 equal to 0. That is T2 minus T1 and extremum. This form of principle of stationary action is the same as the Fermat's principle, which states that a ray of light travels between 2 points along such a path that the line time taken is the extremum. Next question 4E. A spherical pendulum consists of a mass M attached to one end of a massless rod of length L, which is hinged at the other end and is free to oscillate in any vertical plane. Using suitable generalized coordinates, write down the Hamiltonian and find the equations of motion for the coordinates. A simple pendulum that is free to swing the entire solid angle is called a spherical pendulum. In a spherical pendulum, bob moves through the surface of the sphere of radius L about the point of suspension, that is the center of the sphere. The constant motion is holonomic, and the constant equations is x square plus y square plus z square equal to L square, actually the surface of the sphere. Here x equal to L sin theta cos phi, y equal to L sin theta sin phi, z equal to L cos theta. Here L is constant, and theta phi are generalized coordinates here. And kinetic energy T equal to half mv square. So this half m r dot square theta dot square plus r square phi dot square sin square theta. And this equal to half ml square bracket theta dot square plus phi dot square sin square theta. Here r equal to constant. And the potential energy V due to gravity relative to the horizontal plane is actually xy plane is the horizontal plane. Then V equals to minus mgl cos pi minus theta. If this bob is below the horizontal line, so if this angle is theta with the z-axis, then this angle is pi minus theta. So this the vertical distance is L cos pi minus theta, and where it is mg. So this below the position of horizontal plane. So this minus mgl cos theta. The Lagrangian L is given by T minus V, that is equal to T minus V mgl cos theta. And conjugate momenta p theta and p phi are given by p theta equal to del theta dot L. So del theta dot L, so half ml square twice theta dot. So theta dot equal to p theta by ml square, and p phi equal to del phi dot L is equal to ml square phi dot sine square theta, and phi dot equal to p phi by ml square sine square theta. The Hamiltonian H is given by summation of k equal to 1 to 2 pk qk dot equal minus L, that is p theta dot plus p phi dot minus L. Put the value of theta dot and phi dot from 2 and 3 here. So after simplification in terms of p theta, p phi and theta and phi, we get H equal to 1 by 2 ml square bracket p theta square plus p phi square cosec square theta plus mgl cos theta. The Hamilton's equations of motions are given by theta dot equal to del p theta h. So this is equal to p theta by ml square, and p theta dot equal to minus del theta h. This is this, and phi dot equal to del phi h. This is equal to this, and p phi dot equal to minus del phi h. This is equal to 0. Just no terms here phi involving phi. So these are the four equations. These are the Hamilton's canonical equation of motions. Next question for D. What are Poincaré integral invariants and Poincaré-Cartan integral invariants? What is the difference between the two? Poincaré integral invariants, the volume of any arbitrary region in the H space is canonically invariant, because the volume J1 equal to double integration over S summation over I dqi dpi taken over an arbitrary two-dimensional surface F on the twice n-dimensional H space is invariant under canonical transformation, and that is double integration S over S summation over I dqi dpi equal to double integration S summation over I d capital Qi d capital Pi, and this invariant one is known as Poincaré integral invariant. And here we consider the canonical transformation small qp to capital Qp, and capital Qi and capital Pi are derived from small qi, small pi. This is the new small q, small p, the old canonical transformation to new canonical transformation q, capital Q, capital P. And the small qi is the generalized coordinates, and small pi is the momenta conjugate to qi. Similarly, for capital Qi and capital Pi. Poincaré-Cartan integral invariant, the volume capital J, double integration is the surface on surface S, summation over I dpi dqi minus h dt, taken over an arbitrary two-dimensional surface S on the twice n plus one dimensional space is invariant under the canonical transformation. So some double integration over some surface S, integration over I, summation over I, dpi dqi minus capital H dt equal to double integration over S, summation over I, d capital Pi d capital Qi minus k dt. Here capital H and capital K are the Hamiltonians in QPT and capital QPT systems respectively. If dt equal to 0 for constant time, the integral 3, this 3 reduces to the integral 1. So the Poincaré-Cartan integral invariance reduces to the Poincaré integral invariance. And main difference is that for Poincaré integral invariance, we have twice n-dimensional space by twice n coordinates q1, q2, qn, p1, p2, pn. But for Poincaré-Cartan integral invariant, we have twice n plus 1 dimensional space by twice n plus 1 coordinates q1, q2, qn, p1, p2, pn, and time t given. And this is that. And there are another version in many books. So this is the some person Poincaré integral invariant, and the Poincaré is the Poincaré integral invariant is the more generalized Poincaré integral invariant. Thank you for watching this video, and the PDF of this note is given in the description box.